President of the Spanish Royal Physical Society, colleagues, welcome to San Sebastian. Welcome to this opening ceremony of the 39th Bienal of Physics. We hope the development of the Bienal will be productive regarding your expectation as teachers and researchers on physics. Esperamos que las actividades que hemos programado, los conferenciantes invitados, la labor realizada junto con las divisiones y grupos de la RSEF permitan comunicarnos sobre física, permitan diálogos y permitan, en definitiva, innovar en física. A continuación, en esta bienvenida, van a participar 3 personas. En primer lugar, el director general de Innovación e Internacionalización de la Diputación Foral de Gipuzkoa, Gurrutxaga, que tiene ahora la palabra. Aprovecho para darle las gracias en nombre de la Bienal por toda la ayuda que ha concedido la Diputación de Gipuzkoa y sin la cual no hubiera sido posible esta Bienal.
Welcome all. On behalf of the Provincial Council of Gipuzkoa, I would like to extend a warm welcome to all of you. Welcome, or as we say in our Basque language, ongi etorriak guzti guztioi. I would also want to thank you because your presence will turn Donostia San Sebastian into the capital of physics during these days, meeting place for the exchange of ideas in one of the most relevant technological fields, which is physics. Junto a las charlas de personas expertas de relevancia internacional, se desarrollarán diálogos de ciencia, tecnología y sociedad que considero especialmente relevantes. En ellas se tratará sobre el papel de la física en la sociedad de este siglo, el siglo XXI. La revolución de la cuántica promoverá en todos los ámbitos económicos y sociales, la inteligencia artificial, el papel de las mujeres en el ámbito de la física y cómo promover su propio liderazgo. Sabemos que en los próximos años se anticipan avances significativos en varios ámbitos de la física que podrían tener un gran impacto en la economía y la sociedad. Estos avances no solo impulsarán la ciencia básica, sino que también promoverán desarrollos tecnológicos que podrían transformar diversas industrias. Y en eso estamos, como por ejemplo, esperamos que los avances de los qubits, algoritmos cuánticos y corrección de errores pueden llevar a la creación de computadoras capaces de resolver problemas intratables con la informática clásica, que las comunidades cuánticas y la criptografía mejorarán la seguridad de las comunicaciones y la transmisión de datos. La física de materiales lleva años trabajando en materiales como el grafeno, que por cierto, en Donosti, en Gipuzkoa, tenemos una empresa productora de grafeno, pues van a revolucionar la electrónica, la energía y la medicina. Los supercomputadores van a mejorar la eficiencia de las redes de transmisión eléctrica, reduciendo pérdidas y costos. Y la nanotecnología, que ya está posibilitando el desarrollo de terapias dirigidas, sistemas de administración de fármacos a escala nanométrica. Estos avances están en el horizonte cercano y prometen no solo cambiar la forma en que entendemos el mundo, sino también mejorar significativamente la calidad de vida y la eficiencia económica de diversas áreas. For those who are not familiar with Gipuzkoa, I would like to say that although we are a small region, we have a great ambition. We are a region with a strong industrial vocation that is committed to technology and excellence in knowledge to boost the competitiveness of our economic fabric. In the past fiscal year, we were once again the region with the highest investment in R&D as a percentage of GDP in the country, reaching 275%, 5/10 above the European average. Although still far from those countries in the north of Europe, like Germany, which we aspire to match during this legislative term. To achieve this, we are promoting ambitious projects in fields such as quantum technologies, particularly quantum computing and biosciences. No construimos nuestro futuro solo con palabras, sino que llevamos décadas apoyándonos a nuestros centros tecnológicos, que son el verdadero motor de toda nuestra economía. Gracias a esta apuesta continuada, contamos con centros tecnológicos diferentes en muchos ámbitos. Y dado que nos encontramos en un acto de física, no puedo dejar de mencionar algunos de ellos ampliamente reconocidos en el mundo de la física, como es el Donostia International Physics Center, el Centro de Física de Materiales, que además van a presentar ponencias en esta Bienal, y el Centro de Investigación Cooperativa también Nano-UNE, o la propia Universidad del País Vasco. Together with the past government and other administrations, we have established a long-term alliance with IBM Research. The purpose of this 7-year alliance is to make Gipuzkoa, the Basque Country, as an international center of excellence in quantum computing, applied research, training, and development. To this end, among other strategic actions, an IBM Quantum System 1 computer with 127 qubits Eagle processor is being built and will be installed in the middle of next year in a building currently under construction right now about 500 meters from here. Our ambition is to make the Basque Country the leading quantum ecosystem in Southern Europe, capable of generating a research talent and innovation ecosystem in quantum technologies, internationally connected so that it can become a hub of attractions for the brightest researchers from around the world and for the development of business opportunities. Como pueden ver, nosotros también confiamos, al igual que ustedes, en la capacidad de la física para construir una sociedad mejor. We appreciate your presence in our territory and encourage you to enjoy both the Congress and our city too. Besides our commitment to science and technology, we are a welcoming society and hope that during this stage you can enjoy our landscape, our cultures, and of course our cuisine. Gipuzkoa stands out internationally not only for being the territory with the highest number of Michelin stars, but also for the excellence of its popular cuisine, especially our pincho bars. Eskerrak eman nahi dizkizuegu gure lurraldean egoteagatik, eta biltzarraz eta gure hiriaz gozatzen eta gozatzea animatzen zaituztegu. Izan ere, zientziaren eta teknologiaren alde egiten dugun apostuaz gain, gizarte abekitsua gara. Eta espero dugu egun hauetan gure pasaiaz, kulturaz eta nola ez gastronomiaz ere gozatzeko aukera izatea. Thank you very much all and welcome to Gipuzkoa. Thank you.
Next will speak is Xabier Ostalaza, the director of the School of Ingeniería of Gipuzkoa. Queremos agradecerle su compromiso y su ayuda a esta Bienal, ofreciendo toda la infraestructura de la Bienal para simposios de una forma desinteresada y además ayudando en la organización. Xabier.
Bueno, antes de empezar, Jenaro, gracias a vosotros por haberme contado, que sois de casa y es un placer. Espainiako Físikako elkartearen presidentea, Foru Aldundiaren berrikuntzako zuzendaria, agintari eta gonbidatuok eta gainontzeko lagunak, nire akordi beroena denontzat. Benetan oso atsegina da niretzat, Gipuzkoako Ingenieritza Eskolaren izenean, Espainiako Fisikako errege elkartearen Bienalaren hasiera ekitaldean izatea. Begibistan dagoen bezala, kongresu honek fisikaren eremu askoetako adituak batzea lotzen du. Bai estatu mailako zein beste herrialdetakoak ere. Gaur hasten den topaketa, honen baitan egingo diren gogoeta eta azterketak bertaratu zareten guztiontzat oso beraz izango direla joan nago. Señor presidente de la Sociedad Española de Física, señor director foral de Innovación e Internacionalización, autoridades y amigos, buenos días a todos y a todas. Decía en euskera que es un verdadero placer asistir en nombre de la Escuela de Ingeniería de Gipuzkoa a este acto de inauguración de la Bienal de Física. El auditorio nos da una idea de que el Congreso está siendo un éxito ya desde su inicio. Según he podido ver en el programa, la Bienal contará con sesiones plenarias impartidas por personas expertas de talla mundial, que tenía el placer de conocer a una de ellas, y diálogos sobre algunos de los principales problemas actuales de la física, además de simposios especializados en diferentes campos. Todo ello permitirá compartir y debatir sobre los avances en investigación, transferencia de tecnología, divulgación y enseñanza de la física. Este último aspecto es especialmente relevante para la vertiente formativa en nuestra escuela. Si algo podemos afirmar del futuro es que las personas que formemos deberán hacer frente a diversos saltos tecnológicos a lo largo de su vida profesional. Su éxito dependerá en gran medida de su espíritu crítico y capacidad de adaptación, estando ambas cualidades también ligadas a una mayor profundización en su formación en el ámbito científico, tanto a nivel de grado como de posgrado. Ladies and gentlemen, good morning. It's really an honor for me to take part as Dean of the Engineering School of Gipuzkoa in this opening ceremony for the biennial of the Spanish Royal Physics Society. I am very happy to welcome you, and I wish you a pleasant stay among us, during which I sincerely hope that the work sessions will be fruitful and interesting. I am quite sure that this will also be an excellent opportunity for the international participants to become acquainted with the Basque Country and the higher values of its society and culture. Thank you again for your assistance and my warmest welcome on behalf of the University of the Basque Country. Special thanks to Professors Gisasola and Nerea for inviting me to this event. Good morning to you all. Mila esker denoi.
The next and the last, but not the least, will be the president of the Spanish Royal Society of Physics, Luis Viña. Agradecerle, por supuesto, todo el apoyo que nos ha dado y toda su labor entre bambalinas, pero muy importante para el desarrollo de esta vida. Luis, por favor.
Hello everybody. It was not clear to me whether to speak in English or Spanish, or I would do the same as the others. Basque, I'm sorry, but I cannot. I could do Galician, but I think it's not the point to do it. The first thing I have to fight with is with my name. It's Viña, only one. It's not the only Viña in the world, but only one who is Viña. But okay, it's something I have to fight again. Always with it. Okay, in any case, it's a big pleasure to be in Donostia, especially if you can escape from the heat of Madrid and come back here. You can sleep at night perfectly, as we did tonight. And it's a pleasure to be in this place, which is completely full. This is a good sign. And it's not only completely full, but it's completely full of young people, which is even a better sign. Okay? So I'm very, very happy to see that the middle age of the participants in the conference is towards the lower end of the range, so it's a big pleasure. Okay? So I'm going to go back to Spanish. Okay? So, bueno, quiero agradecer en primer lugar tanto a la Diputación como a la Escuela por toda la labor que han hecho para que esta Bienal fuese posible, y evidentemente a Jenaro y a John, que es los que lo han hecho realidad. O sea, la Real Sociedad, es verdad que si hay algo que se necesita, aquí estamos de apoyo y de backup de todo el asunto, pero todas estas bienales siempre se dejan en manos de los organizadores sin ninguna interferencia, creo que Jenaro puede confirmarlo eso, sin ninguna interferencia por parte de la sociedad. O sea, cada organizador de la bienal es libre de hacer lo que crea. Y está claro, como se puede ver del programa, que han hecho excelentemente bien, ¿no? Lo veremos a lo largo de esta semana, pero han hecho excelentemente bien. El número de invitados y la calidad de los invitados y las ponencias y el número de simposios que hay organizados es increíble y demuestra que la Bienal está viva y que va hacia adelante. No quiero meterme en los detalles de todo lo que va a haber en la física, porque de hecho John ha hecho una cosa magnífica, ha dejado claro cuál es el papel de la física y dónde está la física, lo importante que es la física. Había voces al final del siglo pasado que decían que el siglo de la física había sido el siglo XX, que el siglo XXI iba a ser el siglo de la biología y de las cosas biomoleculares. Yo creo que siguen siendo la física y la bio también está ahí, es muy importante, y la unión de las dos es todavía más importante, pero la física sigue jugando un papel y lo seguirá jugando para el placer de todos nosotros, para poder seguir contribuyendo a esto durante muchos años. Bueno, esta, como hemos dicho, es la 39ª Reunión Bienal de la Sociedad Española, de la Real Sociedad Española de Física, que se hace también con el Encuentro Ibérico de Física, donde participan profesores del grupo de enseñanza y división de la física, tanto de España como de Portugal, y digamos, es abierta a que cada uno de esos grupos y divisiones de la Real Sociedad organice sus propias reuniones, aparte de estas charlas invitadas que tenemos durante las mañanas y que se celebrarán aquí en la escuela. Lo que decía de la física también, lo ha mencionado John de pasada, sabéis todos que ya está aprobado por la ONU, que el año próximo será el año del International Year of Quantum Physics and Technologies. Quiero decir que España ha jugado un papel muy relevante, y gracias a la embajadora que tenemos ahora de España en las Naciones Unidas, que a petición, entre otros, y con gran esfuerzo por nuestra parte de la Real Sociedad Española de Física, le pidió que apoyase esa declaración de año internacional, y así lo ha hecho, y esperemos que entonces todos tenemos una magnífica oportunidad para poder contribuir a eso desde nuestro país también, y espero que los distintos grupos especializados en divisiones de la Sociedad Española de Física contribuyan también a eso. Creo que no quería decir nada más, no se me olvida nada importante. Bueno, sí, se me olvida algo, yo no soy muy aficionado al fútbol, pero ayer estando aquí con lo que había que verlo, y hay que dar gracias al País Vasco también, ¿no? Porque de hecho creo que los dos artífices de los goles eran o bien vascos o bien jugando en un equipo vasco. Y ya digo que no estoy muy seguro del fútbol. Y sí quería decir una cosa más. Y quería decir lo que ha dicho John también, que yo creo que en el País Vasco sí tenemos un ejemplo del, ¿cómo se dice en español? Commitment, de la apuesta que se hace en una comunidad por la ciencia y por la física, y con los centros, y Ikerbasque, y los GUNE, y todas esas cosas, que es una envidia para muchas de las otras regiones de España, y que es un ejemplo a seguir, y que esperamos que se pueda seguir en el futuro. Y nada más, deciros que en realidad la Bienal es vuestra, o sea, aquí estamos todos para que vosotros, con vuestras participaciones y vuestras comunicaciones, nos enseñéis y aprendamos todos los que estamos aquí, y que otra vez es un placer estar en Donosti, y muchísimas gracias por recibirnos a todos aquí para la Bienal. Gracias.
Bien, con esto terminamos la ceremonia de inauguración. Un aviso y comenzamos ya con el primer conferenciante. El aviso es que a las 10:30 nos reuniremos todos en la puerta de la Escuela de Ingeniería, justo aquí enfrente de Musiquene, para hacer la foto del congreso. And with that we close the
digo que no tenía claro cuál era la lengua de la conferencia, entonces la presentación de Ignacio me la he preparado en español. La podría ir traduciendo en inglés, pero bueno, creo que se entiende si la hago en español también. Bueno, en realidad es un honor presentar en nombre de la Real Sociedad Española de Física el primer conferenciante plenario de esta 39ª edición de la Bienal de Física y también el hacerlo en Donosti, como acabo de decir, ya que es siempre un placer disfrutar de esta ciudad. ¿Qué se puede decir de Ignacio Cirac que no conozca ya la audiencia? Pues muy poco, la verdad. Ignacio es una figura clave por sus investigaciones en computación y óptica cuántica, como vamos a ver. Ignacio se licenció en Físicas en el 88 en la Complutense, se doctoró 3 años más tarde con una tesis sobre la interacción de átomos de 2 niveles con estados no clásicos de luz, bajo la dirección del profesor Luis Lorenzo Sánchez Soto. Después ejerció como profesor titular en la Universidad de Castilla-La Mancha hasta el 96. Durante este tiempo también hizo una estancia postdoctoral en la Universidad de Colorado en Boulder. Y más tarde, hasta el año 2001, fue catedrático en el Instituto de Física Teórica de la Universidad de Gipuzkoa. Y desde el año 2001, es decir, desde hace ya 23 años, es director de la División Teórica del Instituto Max Planck de Óptica Cuántica en Garching, en Alemania. Además de sus intereses en teoría cuántica, ha investigado sobre gases cuánticos degenerados, sistemas atómicos fuertemente correlacionados y sistemas óptico-cuánticos, con más de 600 artículos y uno de los autores más citados de su campo. No tenemos tiempo suficiente para citar aquí sus innumerables premios, pero sí quisiera resaltar que además de poseer 8 doctores honoris causa, primero quiero empezar con los premios que tienen que ver con la Real Sociedad. De hecho, en el año 1992 tuvo el premio de investigadores noveles de la Real Sociedad Española de Física y 10 años más tarde la medalla de la Real Sociedad Española de Física. Desde ese año también, desde el año 2002, es miembro de la Academia Española de Ciencias. En el año 2006 recibió el premio que se llama ahora Princesa de Asturias, en aquel momento Príncipe de Asturias de Investigación Científica y Técnica. En el 7 el Premio Nacional Blas Cabrera y en el 2008 el Premio de Fundación BBVA Fronteras del Conocimiento en la categoría de Ciencias Básicas, compartido con el profesor Peter Soller. Tengo que decir también que los premios de las Fronteras de Conocimiento se caracterizan por su gran capacidad de predicción de premios Nobel, lo cual sería bueno que en este caso también se hiciese realidad. En el año 2013 recibió otra vez con el profesor Peter Soller el premio Wolf en Física y desde el 2017 es miembro de la Academia Alemana de las Ciencias Naturales Leopoldina y en 2018 recibió la medalla Max Planck y podría seguir con otros muchos más, pero creo que lo importante es que nos escuchemos lo que Ignacio nos va a contar. No quiero entretenerlos más ni privarlos de la oportunidad de escuchar a Ignacio en su conferencia sobre Quantum Technologies, a Dream or a Reality. Ignacio, el estrado es tuyo.
Hola, buenos días. En primer lugar, me gustaría agradecer a los organizadores por haberme invitado a estar aquí otra vez en Donostia, un lugar que visito bastante a menudo por mi amistad que tengo con el IPC. Y bueno, también me gustaría agradecer a Luis por esta amable introducción. Muchas gracias. Y bueno, I'm going to switch to English because I think that there are some guests here who speak English and probably don't speak Spanish. And I'm going to talk about quantum technologies, and the title is A Dream or Reality. And the reason why I gave this title is because it paraphrases an article that was written in 1998 by Serge Haroche and Michel Raymond, so the first one became a Nobel Prize some years ago, which was called Quantum Computing, a Dream or a Nightmare. And at the time, the reason behind that was that some proposals and some proof of principle experiments took place, and there was many people saying that quantum computing could be something that would revolutionize basically physics or science or even computer science right away. And at that time, these authors wanted to protect a little bit the area, claiming that it was fundamental research, but they went even a step forward or a step beyond. So they claimed that quantum computing was impossible, and that's why they said it was a nightmare. So now we're here, and I think that we no longer think that quantum computing is impossible, but it's still a dream, even though it has some reality in it. And that's what I want to show here. So situation that we have now, quantum computing, especially in quantum simulation, but also in quantum technologies and what are the prospects. So let me Okay, so the first thing is that so people, when we talk about quantum technologies, think right away about quantum computing, but quantum technology is much more than quantum computing. Quantum computing is just a part of quantum technology. So quantum technologies use quantum physics in order to process, transmit, or to acquire information, and that's why quantum technologies have applications in computing, has applications in communication, applications in detections, in metrology, and there is a lot of research and development in all these fields that are building already some devices that we have now. So you can see in the picture some devices that are related. The first one is a quantum computer, similar to the one that we installed here, and the one up there is a quantum communication scheme. The one down there is quantum geometry, so it measures G, small g. The other one is an atomic clock. You also have some satellite-based quantum communication, random number generations, and so on. So with that, I wanted to emphasize the fact that even though when one says quantum technologies, one always thinks about quantum computation, that is much more, and it's being developed at the moment. Okay, so there are many interests now in quantum technologies. So you can read in newspapers every day that there is a breakthrough basically in the field. And this has attracted corporations, big corporations like IBM, that will bring some of their computers here, but also many others all around the world are putting a big investment in quantum technologies. There are also many startups growing. So if you look at the numbers, you see that in the last couple of years, per year there was about $2 billion invested in quantum technologies. These are the official numbers, so probably it's much more because not everything is declared, and that has been growing during the last years, as you can see there. And so, for example, there are some companies, startups that went even to the market, so they are now in the stock market, and they have a value of $2 billion. And that's not only corporations, not only startups, not only private investment, but also there is, it's not working very well. But also there is a lot of public investment, so it's an order of magnitude is $40 billion in quantum technologies, and so you can see that there is a lot of money invested, especially in places like China, Germany, the US, Europe also to some extent, and it's now in Spain and in the Basque Country. In the last years have been also a lot of money. Anyway, so this shows that there is a lot of interest, not only in science, but also in public institutions, also in the industry, also in the investors in quantum technologies. And so why is that? So why do people think that that's something that's going to change the world and make something good for mankind? And it's because people think that all these quantum technologies will have applications in different areas. For example, in the pharmaceutical companies, by drug design, so quantum computers may help to design new drugs. So financial services, because quantum computing is also supposed to help in order to optimize things on portfolios, fertilizers, and because also quantum computers may help in chemistry, materials, and batteries. Again, because we believe that quantum computers can help design better materials in machine learning and artificial intelligence. Again, the same reason, logistics, also in medicine, so here's because of the sensors that are being developed, the quantum sensors will probably go beyond the capabilities of the ones that we have right now, and telecommunications because of quantum communication. However, one has also to recognize that there is also a big hype in quantum technologies, and now you can see in newspaper, so statements like this one here, that basically quantum computing can do everything, and that's not true. So honestly speaking, we know that quantum computing is something that is very powerful. We know certain applications, we have many hopes, but also many expectations. But the reality is that we don't know many of the things that have been promised. We have some indications about that. And in order to be a little bit more precise, so in the context now of quantum computing, we concentrate on quantum computing, we know that quantum computers, if we're able to build them, could help us in some specific problems. So the first one are related to cryptography. So we have a quantum computer, then we could decipher all the cryptographic methods that are used nowadays. The second set of problems is in optimization. So an optimization is something that is very used in the industry, and optimization example is the traveling salesman person, where you have a set of cities, you are reviewing the distances among them, and then you have to find the shortest path that visits all the cities. And like that one, there are many other optimizations. So at the end, you want to optimize resources, you want to optimize maybe the path, and maybe you want to optimize, I know, for example, BMW in Munich, that's where I live. They have robots that paint cars, and they have many arms, and so in order to paint as fast as possible, they have to make sure that they don't cross each other, and that's an optimization problem. So how to paint as fast as possible without having these crossings, that's again an optimization problem. And like that in the industry, there are very many, and we believe that the quantum computers can help us in optimization as well. Also in data analysis, in machine learning, so we have many data, and you want to maybe learn something, or you want to make decisions, to take decisions, as it's done in machine learning, and we believe that quantum computers can help. But probably the most clear application of quantum computing that we know very well is in quantum simulation. So we want to solve scientific problems related to quantum physics or quantum chemistry, then quantum computers can help us. And you see this diagram that I wrote there is for applications. Then there's a big difference between the left side and the right side. So the scientific problems, the simulation, we know there that quantum computers can help us a lot. So there are problems that without quantum computers we will never be able to solve, whereas with quantum computers we will be able to solve. And that's because there is an exponential speed up with the size of the problem, and that's something with respect to classical computers, and that's a huge difference that can make. So there are computations that even in supercomputers you cannot do in the edge of the universe, and with a quantum computer we could do in hours. The ones on the right are a little bit, they are not, so there's not such a big advantage. It's what we call polynomial advantage. So we know that there are quantum algorithms that solve them better than classical computers. However, it's not clear so how much better. It's clear that it will be better, but it's still under debate, so how much. We hope, however, that what will happen is what happened if we look back in history, when we had the first classical computers, that at the beginning, the only applications, or basic applications that they knew about that was in the 40s, in the last century, were to solving some specific problems related to cryptography. At that time, it was the Second World War, and they developed the computers just because they wanted to decipher the messages that were sent. And it had also applications, scientific applications there, but at the time they didn't know all the applications that we have right now with classical computers. And the hope is that with quantum computers the same thing will happen, that we know now a couple of applications very well, but once we construct, once we build, once we play with them, then we'll find many other applications. So after this introduction, what I want to do is to concentrate on quantum simulation and to tell you a little bit about the state of the art and some applications and so what is going on the field, which is probably the one that has in the short time most of the applications or most of the success in quantum technologies. Okay, so it was realized already many years ago by people like Dirac in 1929, that once we have the laws of quantum physics that are dictated by Schrödinger equation, then the problem is not solved. So you have now, and you want to apply these laws to specific problems, then, I mean, you will have a big problem, and the reason is because these equations are very complex. So as soon as you have many objects and you want to describe with quantum physics, then this requires a lot of computation. And now Feynman, many years ago, about 60 years after that, they actually formalized it in a better way and realized at the time, it was the time where they were developing quantum chromodynamics, and so they were developing methods to solve them in lattice QCD appeared at that time. And they realized that it was, classical computers were very difficult to solve those problems that appear in quantum physics. And so what he formalized is that the fact that if we have many particles, like it occurs in quantum chromodynamics, or that it happens in chemistry, or it happens in many other fields in physics, condensed matter physics, and you want to describe them using quantum physics, then you will run out of resources very soon. So they're very complex to solve with classical computers, and that's where he proposed to use quantum computers. So in fact, in that paper, he coined the term quantum computer. So he also described qubits. He didn't call them qubits, but he explained that what you should do is to discretize space. If you want to solve a problem, discretize space, put a two-level system, a qubit in each side of your lattice, and then describe the dynamics of the system just by doing what we call nowadays quantum gate. So he fully described what is now a quantum computer. So again, he said that if you try to solve a quantum problem, a quantum many-body problem with a classical computer, then you will have many problems in resources, so your resources will grow exponentially with the number of particles of the size of the system that you have. Whereas if you had a quantum system to solve that problem, then this will not happen, it will be much more efficient. And indeed, so you have one of the problems that appear in chemistry, condensed matter physics, or high energy physics. So when we want to describe it and make computations and make predictions about its behavior, so the first thing is that we put it on a lattice. So in the case of chemistry, then we have, for example, some natural orbitals, and they do write everything in terms of these orbitals, which is some lattice. In the case of condensed matter physics, then the system itself has some periodicity and forms a lattice. So then you will put in each of the, for example, you're describing electrons, and you put some electrons at each of the lattice sides. If you're in high-energy physics, then you discretize space in the way that Klein was saying, and then again, you will discover at the end everything on a lattice. So at the end, a problem in quantum many-body physics can be fully described as a lattice problem, where you have qubits on a lattice or some n-level systems in your lattice, and so the physics will tell you what is the Hamiltonian, so how they interact with each other. And so at the end, what you want to do is to describe so how it will behave in the future, what are the properties in thermal equilibrium, physical properties. And for that, in quantum physics, what you have to do, you want to make predictions to calculate what is the wave function. So you have to write your wave function, and this wave function, according to quantum physics, would be a linear combination of all possible configurations. So it would be a configuration, for example, you have the spins in your lattice, configuration with all the spins are up, and all spins up and one down, and two down, and so on. And then you can count that there are 2 to the power n configurations, in this case that you have spin 1/2, in this case you have qubits. And if you want to tell me what is the state of your system, you will have to tell me what are the complex coefficients that appear in front of each configuration. So all the physical properties are encoded in this complex coefficient. So if you want to make any prediction, you will have to compute this complex coefficient. And since there are 2 to the power n, then you will have to give me 2 to the power n coefficients. So this means that if you have a computer where you're doing the computations, you will have a memory that has to scale exponentially with the number of particles that you have. And also, because you will have to store all these coefficients, and at the same time, if you want to compute this coefficient, you will have to do at least 1 computation per coefficient, and since there are 2 to the power n, then you will have to do 2 to the power n computations, and this means that you will have to take a computational time that will also grow exponentially with the number of qubits. So we have a very strong situation in which if you want now to solve this problem, this many-body problem with a classical computer, you will run into 2 big problems. The first one is that your memory will have to grow exponentially with the number of particles that you want to simulate. And the second one is that the computational time will also grow exponentially. And so you put just some numbers, then you realize that current capabilities allow you to go to something like 40 two-level systems with the classical computers. If you go to 50 or 60, then it's basically impossible to make predictions to compute all these coefficients. And if you put 300 particles, if you want to describe the behavior of 300 qubits, then you need a memory in time that will scale like 2 to the power 300, and 2 to the power 300 is basically 10 to the power 80, which is the number of baryons in the universe. So this means that if you would like to store now these coefficients in a classical computer, just of 300 qubits, then you will have to use the whole universe as a computer just to store it. And this shows already what is the power of quantum computation in solving quantum many-body problems. Quantum many-body problems, there are some problems that we will never be able to solve just because of this exponential scaling. And as Feynman proposed many years ago, if you use a quantum computer, then you will be able to solve them. And the reason is that what he proposed is, in order to store these wave functions in classical computers, namely all these coefficients in a classical computer, let's take now a quantum system, a quantum computer, and we want to simulate, we want to solve a problem of n qubits. Let's take another system that has exactly n qubits, and instead of storing the coefficients, let's prepare our quantum computer in the state that we want to investigate, and in our quantum computer, and once we have it, let's measure there, and with that make the predictions. And so this means that if you want to solve this problem, instead of using 2 to the n memory, 2 to the n time, then you will use only n qubits, and therefore this solves right away the problem with memory. And that's a very big, this makes a very big difference with respect to other applications of quantum computers. So as I mentioned before, quantum computers can be solved for machine learning, can be solved for optimization problem, but in those cases, the problem is classical, so you don't have to store superposition, you just have to find one configuration. And maybe a quantum computer can help you with that. But here in quantum many-body problems, right away you gain a lot, you gain exponentially, just because just formulating the problem, trying to put it in a classical computer, you see that it's impossible with classical computer, and that's why quantum computers will be very helpful, quantum simulation will be very helpful, or quantum computers will be very helpful in quantum simulation. So now, there are two ways in which people are building these simulators. So quantum simulator will be now a quantum computer that will be devoted to solve these quantum many-body problems by using the ideas of Feynman. And so now there are two paths that people are following. So one is an analog way. So what you would like to solve a problem, somebody gives you a Hamiltonian on a lattice. What you do is with your quantum system, you just build it on a lattice and engineer the interactions in your system in such a way that they resemble or they correspond to the problem that you want to solve. And once you have done that, then you just leave your system alone, and after some time you measure, and in this way you will simulate the dynamics and will be able to make predictions about the dynamics of that system. The other method is digital, is build a quantum computer based on qubits and quantum gates, and now just discretize a little bit the time, also not only the space, and solve it like that. And each of them have their advantages, so the analog are easier to build, there is more natural for fermions, and then you don't have to discretize time. It turns out that that's very important for the errors, if you have some errors in your quantum computation, as I will mention later on. Now the digital, it has advantage that it's universal, so you can solve any Hamiltonian there, you can solve any problem with that system. Also, there is possibility of correcting the errors by fault-tolerant error quantum computation or error correction. However, they are much more difficult to build in practice, and so it will take a long time until we have this fault-tolerant quantum computer. So from now on, I will concentrate on analog quantum simulation that is now pursued in many labs around the world. Okay, so I'm going to talk about analog simulators. And there are many physical systems with which people are building analog quantum simulators, also digital. So we have Trapius, and I think that Jonathan Hom will talk about this quantum computer based on Trapius. We also have photons, tabletop integrated systems. We also have neutral atoms in optical lattices or brickwork and tweezers. We have superconductors with different kinds of superconducting qubits. We also have embedded atoms in the solids or semiconductors and quantum dots. And there have been very interesting experiments in the last 3 to 4 years in quantum simulation with all the systems, but here I will concentrate on neutral atoms. That's the one that is closest to my heart, and it's at the moment also the one that is most advanced. So the idea of cold atoms in optical lattices was brought up in 1998 in some collaboration with Peter Troller, in fact. And the idea is that if you take now atoms and alkali atoms, and then you cool them down to very low temperatures, if these atoms are bosons, then they will create a Bose-Einstein condensate. And if they're fermions, then they will be in a Fermi-Dirac distribution at very low temperatures. And once you have them very, very, very cold, then what you can do is to switch on an optical lattice. So you switch on to counter-propagating laser fields to make an interference pattern. And it turns out that these atoms are like very little electric dipoles, so they feel the intensity of this electromagnetic field, of the electric field of the laser. So they will be attracted to the regions of maximal intensity and will be repelled from the regions of maximal intensity. And so this is why they will see a potential that would correspond to this standing wave. And now you can do this in 3 dimensions. You can have your atoms trapped in 3 dimensions, or you can trap them in 2 dimensions, and so on. And now, when the atoms are trapped, they're levitating basically, then they can move from one potential well to the next one. They can hop by tunneling, and so they behave very much in the same way as electrons move in solids. And in fact, when 2 atoms meet at one of these potential wells, then they interact. And the interaction is very much like the interaction that occurs in solids. And that's why this was right away viewed as a proposal for a quantum simulation of electrons or even bosons. And therefore, I mean, there was an experiment done in 2002 in the group of Immanuel Bloch in the institute where I'm now, where they were able for the first time to observe something related to this prediction of simulators. So what they did is that they pulled down the atoms and they put them on the lattice, and then they observed that depending on whether the interactions were strong or weak, they could see like 2 phases of matter. In the first one, the atoms behaved like a superfluid, okay, so they were distributed and coherent along the whole, let's say, trap. And in the other regime, they formed what is called a multi-insulator, so there was an atom per each lattice size, and in that case, there is no coherence, and that's why they observed some time of flight interference patterns that indicate that they had a superfluid. They observed the peaks that you see there and indicate that they had a multi-insulator that you can see that. And that's the first realization of a quantum simulation where they simulated what is called the Bose-Hauer model with cold atoms in optical lattices. At that time, it was known that this problem can be solved with classical computers. So there are some problems that, for example, using Monte Carlo can be solved with classical computers, and that's what one of the first one. So this was nothing. This was not an experiment where they were able to solve a problem with the quantum simulator that you cannot solve with classical means. But it was more or less to benchmark and to realize that with this system, indeed, you could do some quantum simulations as long as you can go to a regime where it's difficult to do it with classical computers. For example, if you would replace the bosons by fermions. So since 2002, these experiments have improved a lot, and one breakthrough in the experiment is what is called the gas microscope. So at the beginning, they had to do this time of flight, they had to release the atoms, and then you see how they expanded, and then detect where they were. But now they can see them in situ, so they can observe with a microscope, and they can see where the atoms are, and not only that, but they can just control them individually. So you have the first picture that was in the year 2010, where they were able to observe the atoms one by one upstairs. Then they also were able to create potentials, not only just these periodic potentials, but the potential that they want using light. And so, for example, in one of these papers in 2010, they were able to write psi and things like that, just the atoms, just putting them in specific positions in the lattice, and then shining light, and then you see the light, and that's what they saw. So this improved a lot. So at the moment, now we have that they can have something like that, so they can create the patterns that we want, so they can create the lattice that you want, put an atom, observe it there, and have them there for a very long time, and control it away. And you go to the lab technician looking in Harvard, and you can see that they can do things like that. How the PhD students spend the time of the college. Anyway, so I mean, this shows that these whole atoms in optical lattices and also in tweezers, in which you now not only have an optical lattice, or not only the optical lattice, but now you focus lasers at different positions, trap the atoms one by one and put them together, make them interact. So this has opened up a new way of doing quantum computation, but also quantum simulation. And with that, then you can try to solve problems that appear in some areas of physics and chemistry. And so people have been proposed and doing experiments about Hubble model and spin models in atoms with optical lattices. That's the ones that I mentioned before, because these atoms behave like electrons moving in a solid. Then you can simulate the physics of electrons moving in solid and the magnetic properties as well as the spin with these systems. Also, one can simulate quantum optical systems, so for example, superradiance or subradiance, or some effects that appear when you have many atoms that collectively emit light. There have been the first quantum simulations of high energy physics. At the moment it's a little bit more difficult, and because these are, again, so when you discretize your system and you write it on a lattice, they resemble very much the problems that appear in condensed matter physics. There are some local Hamiltonians that interact with each other. However, the problem is that you have some flux terms in the system, meaning that you have to have four-body interactions. And so the nature does not provide us directly with four-body interactions, but with two-body interactions. In order to get four-body interactions out of two-body interactions, then we have to do some perturbation theory, to fourth-order perturbation theory, where everything is very weak, and that's why these experiments for the moment are relatively difficult, and they have only been observed some high-energy physical behavior in one-dimensional systems. And so lately, one can also simulate what's called atoms quantum chemistry problems, and I want to say a couple of things about that, because this is a problem I've been lately involved. Okay, so how can you simulate quantum chemistry with cold atoms? Well, you have a problem in quantum chemistry is sometimes it's formulated in the following way. So you have some nuclei, and then you have that are at some positions in space, and then you have some electrons moving around. And what you can do is the Born-Oppenheimer approximation, in which you assume that the mass of the nuclei is infinite, then you fix them in space at certain positions, and then you solve the electronic problem and find what is the ground state at given these positions of the nuclei. Now you change the position, and then you compute again what is the ground state. Then you change the position and the ground state, ground state, ground state. And so then you can plot as a function of the position of the nuclei what is the energy, and this will give you an energy landscape. So for example, you have two particles as a function of the distance. You can look at what is the electronic energy, and then you will find that there is this dissociation curve, molecular potential. And once you have calculated this molecular potential, then you can see what is the equilibrium position. So where this, at low temperature, this nuclei will stand, and then you can also study now electronic transitions and so on. And so that's one regime of quantum chemistry, and so that's what we think that we could solve with cold atoms in optical lattices. So the basic idea is, so how do we simulate that with cold atoms? So the first thing that you have to do is that you have to replace the electrons by atoms. And that's possible because they are fermionic atoms. It's important that the electrons are fermions, that they have Pauli exclusion principle, but they are fermionic atoms. So then the atoms will represent your electrons in this simulation. Now, the electrons have to move, so they have to have some kinetic energy, but it's simple in optical lattices because as I mentioned before, these atoms can move in the optical lattices. The only thing is that this corresponds to a discretized version of the motion of the electrons, but that's fine. If you have a system that is sufficiently large, then you can go to the continuum limit. It's something that can be computed very well. Now the next thing is that these electrons that move have to be attracted to the position of the nuclei. So now you go to the quantum simulator. What you can do is that if you decide that there is a nucleus here, then you can focus a laser, and using holograms, then you can make an optical potential, so the intensity pattern, in such a way that the atoms are attracted to the maximum intensity, and the law of attraction is 1/r. So this can be done with holograms. So this means that now you put a laser focus here, another laser focus here, another laser focus here. It will be as if you have a nucleus here, a nucleus here, and a nucleus here, and then the electrons can move and be attracted to this nuclei with the loss that, with the Schrödinger equation, with the corresponding law of chemistry. So the most difficult part is now the electrons, they also have to interact with each other. They have to repel each other. And that's much more difficult. And it's much more difficult because atoms are neutral. So they don't basically interact. They only see each other if they're in the same position. So how do you make now that the each other, and even with a 1/r potential. And in order to do that, what you can do is to imitate nature. So you studied quantum electrodynamics, then when you studied what is the force between electrons, and you see that the electrons are coupled to the electromagnetic field in quantum electrodynamics. They don't have a direct interaction. So what they do is that they interact by exchange of photons. They are coupled to the electromagnetic field. One emits a photon, it's absorbed by the other one, this gives repulsion. So what you can do is the same thing in atoms in optical lattice. You can couple these fermionic atoms to some other bosonic atoms that are there, that play the role of the electromagnetic field of the bosons. And if you design the interaction appropriately, even if it's local, between the bosonic and the fermionic atoms, and you are able to go to a regime where you can eliminate the bosonic degrees of freedom, then you get an effective interaction, and you do it well, then you have this repulsion that goes like 1/r. So that's what we proposed several years ago, and during the last year, so that it turns out that that's difficult experimentally, but so what we have done is to simplify, and so for example propose to start in 2 dimensions instead of 3 dimensions, because the experiments in 2 dimensions are simpler to control and also to focus these lasers and so on. Also, instead of using this method of getting the interaction between the fermions mediated by some bosons, what we thought is that maybe in the beginning it would be better to have a direct interaction by promoting these atoms to Rydberg levels. In the Rydberg levels they have some dipole moments, so they interact with dipole-dipole interactions. This interaction behaves like 1/r³ or 1/r⁶. It is one-to-one interaction, so it's not the same as it occurs in chemical systems, but still, what you can solve is in these systems that could be much simpler because there are many experiments now with Rydberg atoms in these conditions that we propose. Did some calculations, making predictions for these experiments, and we saw that they could see the physics of hydrogen atom, hydrogen molecules, even three hydrogen atoms and so on. And we cannot make predictions about what they will see when they have, like, say, 5 hydrogen atoms, because we run out of classical resources. We don't have a quantum computer to make that, and so that's why we believe that those systems will be very useful in order to do some calculations that we cannot do with our classical computers. So some experiments are underway, and I hope that in the next couple of years or so we will see experimental quantum chemistry with cold atoms in optical lattices. So that's a new regime for cold atom experiments, and the reason is that so far the ones that simulate, let's say, condensed matter physics or high energy physics, then you have to have many atoms, so some density of atoms, so like let's say 1 atom per lattice side. Well, that this quantum chemistry work in a different regime, we will have very few atoms, as few atoms as electrons. So we may have a lattice that is 30 by 30 and have only 20 electrons because we want to simulate only 20 electron systems, not 400 sites. Okay, so now, how much time? About 10 minutes? Okay, so now I'll talk 5 plus 5. Okay. So I'll talk about quantum simulations, distributive systems. So that's some work that we've been also doing during the last years. And so here, I mentioned that in quantum simulation you're giving a lattice, you're giving a Hamiltonian, and then you want to make predictions about that. So now we change a little bit the problem. So it turns out that in many systems, the problems that we face are open quantum systems. So you have a system that is interacting with the environment, and then you would like to make predictions of what will happen with your system now in the presence of the environment. So there's no longer a system that is driven by a Schrödinger equation, but is driven in terms of something that is called a Lindbladian, it's called a master equation. And so what you would like to do now is to simulate master equations in many-body systems. So again, you will be given some, instead of Hamiltonian, the equivalent in dissipative systems, which is called Lindbladian. You're given some Lindbladian, some operator, you're given some initial state, you're given some time, and then you would like to make a prediction. So what will happen with the dynamics, or what will happen with the system after some time? It will be the physical properties of that system, or maybe in steady state, you have an open system, then you have a fixed point, so you go to a steady state, and you would like to make predictions about the steady state. And so typically some observer would like to measure the magnetization, let's say, in a steady state system. And already many years ago, so we wrote a paper in which we showed how you could do this quantum simulation with analog systems, and the idea is just to take the system that you want to simulate, these are the blue dots, and add some other atoms there, this would be the red dots, and to dissipate these red atoms. So you can do it, these are atoms, for example, shines some light, except for that there is spontaneous emission. This will give dissipation, and if at the same time you couple the red atoms to the blue atoms in the appropriate regime, you can eliminate the red atoms and you have an effective dynamics for the blue atoms that corresponds to the master equation that you want to simulate. So that's universal, that's a universal way of simulating open manual systems in which you just have to add some additional, let's say, qubits that are giving the dissipation to the system. And so the questions that arises is, so can we talk about quantum advantage in that system? So can I make a claim that with a quantum simulator, I'll do better than you use a classical simulator? And in fact, there are two ways of looking at this problem. And so there is the physics problem, in which if I solve this with my, let's say, with my quantum simulator, and at the end I get some result, then I will challenge you and say, well, try to use your classical computer and beat me. And this will depend, of course, on your capability of using classical computers, on the algorithm that you will use. And so maybe what I say, let's compare with the most advanced algorithm that we have. And then, in this way, if I'm faster with my quantum simulator, I will say that I have quantum advantage. However, I mean, that's not, I mean, computer scientists don't like this point of view, because it may happen that tomorrow there's another one that comes with another classical algorithm that is much better than the one that you're using, and then you beat me again. And so then we say, well, let's say it depends on the algorithm. There is a way that computer scientists use in order to overcome this problem, is that they look at problems that they consider to be extremely difficult, because people have worked for 50 years to find algorithms to solve them, and they have not been able to solve them. And then what you show in order to state that you have a quantum advantage is that you say, well, if I have now, if I do something, and you're able to replicate with a classical computer in the same time that I use in my quantum computer, then you can use your classical algorithm and solve these problems that nobody believes that you can solve. Or for the experts, so if you're able to simulate with your classical computer what I'm doing with my quantum simulator efficiently in the same time that I do it, then you will also be able to factorize numbers, you will be able to solve optimization problems, you will be able to use to have all the advantages that we believe that quantum computers have with respect to classical computers. And this makes robust the result, because then you say, well, either, okay, so it's very unlikely that you will be able to compete with my quantum computer, but you are able to compete. It's great, because then you have solved the problem for everybody, because you will have now that classical computers are as powerful as quantum computers. And so that's basically what we have done. So maybe I will not tell you the details because I don't have time. And so we have shown that there are problems in steady state of open quantum systems that if with a quantum simulator you could solve them in time that, I mean, it's maybe linear with the size of the system. However, if you want to solve it with a classical computer, it will take an exponential time with the size of the system. And if you find an algorithm that it doesn't take an exponential time, then this means that you can use that algorithm to do anything that a quantum computer can do. So this makes it very robust, the problem of quantum computing. And the second thing is that you can think what happens in the presence of errors. So now the quantum simulators are not perfect, they have errors, there is no error correction. And so what we have been also proven is that imagine that now I do a quantum simulation with a quantum simulator that is not perfect, and then I get a result. And this result is not perfect. Okay, so because my simulator is not perfect. Now you have a classical system, which is able, classical computer that is able to get the same error that I have. And it takes, for example, 1 million of steps, 1 million of interrogation in your classical computer. So what we show is that now you improve your software by a factor of 10, then the classical method that you're using will scale like the number of steps that you have to the power 10. So it's exponential with my improvement in hardware. Or in other words, if I improve my hardware by a factor of 10, I will make all the errors at 10% of the error that I had before. Now the classical computer, instead of taking 10 to the 6 steps, would have to take 10 to the 60 steps. It will be impossible in practice. So this again makes also very robust the results of quantum simulators, even if there are errors in the experiments. And so with that, I think that I'll go to the conclusions. And okay, so quantum simulation is arguably one of the most suitable applications of quantum computers. Analogs, quantum computation and quantum simulation. Now, it's relatively powerful and it's very well suited simulate physics and chemistry problems, and maybe something that is also important, that quantum technologies, and in particular quantum computing, still requires an effort of basic research. And with that, I will finish, and thank you for your attention.
Thank you very much, Ignacio, for the wonderful talk, which is now open for a very short discussion because the organizers are very eager to keep it, and we recombine here at 11 o'clock. So we should have 15 minutes of coffee, but there is still time for a couple of questions. Any, please? Well, there's one here.
Thank you for the presentation. You said that quantum simulation is work well for quantum problems, but can we also use for other kind of classical simulation, like for example solving Navier-Stokes equations, something like that? Is it possible to do that, and how?
Okay, so analog quantum simulation has problems with that, because first you will have to rewrite Navier-Stokes equation as a Schrödinger equation. You can do that, which is typically not possible with partial differential equations, then you will not be able to use quantum simulation. Quantum computation can do that, so in fact there are algorithms for partial differential equations, and then people have proposed algorithms for Navier-Stokes equations, but in those cases the gain is not exponential, the gain is polynomial, and so that's as far as I know.
I have a question myself. So I think you made it very clear that this quantum simulation is quantum computing, and you just stay on the side of the quantum simulation. But people are still dreaming of the quantum computing. So can you say a couple of words about it?
Yes. So maybe I show this. That's the roadmap.
I was not prepared.
So that's the roadmap for quantum computation and quantum simulation. So you see that in '96 there was the first prototype. There was this paper of quantum computer dream or a nightmare. Now 2019, Google had the first experiment where they showed that they could do something with a quantum computer that nobody could do with a classical computer at that time. And now we have entered what is called the NISQ area. So these are the quantum computers like Google one, like IBM, like many others, that still have errors, are not perfect, but they're getting better and better and better. And so now the focus of research there is to see what can we do with these quantum computers that still have errors, but for some problem they may be so powerful that even in the presence of errors they are more powerful than classical computers. That's what happened, for example, with the Google experiment. And now people are starting now correcting the errors in quantum computers. So there has been a breakthrough last year in the group of Harvard in QERA that they were able to create some error correcting code and to correct 40, they had 40 logical queues and do some correction. And so if things go like these people think, then they say that in the order of 5 to 10 years, then they will be able to do fault-tolerant quantum computation. So maybe in something like 10 years, we have fault-tolerant quantum computers, meaning that we'll have quantum computers. We will not need maybe quantum simulators anymore, because then we'll have something that works directly in a discretized way, in the same way that classical computers work in a digitalized way.
Any other urgent question? Yes, there is one right across, I think.
Yes, you have said at the beginning that you can now see the position where your atoms are with a microscope. Is this a transmission electron microscope? When you use it, you don't manipulate. So how does it work?
Oh, that's actually, so the distance between the atoms is of the order of half a wavelength. And so what you can use is some other wavelength on the first side in order to see to focus the atoms. And what you can also do is the statistic, like we do in microscopy. So you measure a long time, and then you look at the image, and then you will know what is coming from one atom and not from the next one, just by doing statistics. So that's what they do. And there are other tricks that is, for example, so you put some magnetic field, then you will create some Siemens shift in the atoms, and if there is a gradient, then the Siemens shift will depend on the position. And so now you rationally can just look at one atom, at certain position because that's the only place where we have certain shapes. So they're using all these techniques now all over the world in order to make microscopy, let's say, to see distance is smaller than the wavelength of the same order of magnitude than the wavelength. It's optical. Everything is optical.
I'm sorry, it's a pity that we cannot continue with the questions, but we are on a rush of time. So thank you very much, Ignacio. We will come back at the end of the
Remember, we will take the Bienal photography now in the School of Engineering.